Hello viewer, this is EasyElimu channel. I'm Vincent Kanwai and today I will be taking you through Form 3 Mathematics. We shall handle Chapter 13 of Form 3 Mathematics, the probability. Please welcome. We shall start with the introduction, and in the introduction we will find out that in our daily life activities we are surrounded by events of which may occur or not occur, but one may be interested in telling the likelihood or chances of that event occurring. And the occurrence of an event may depend on the past experience of which the event had happened earlier. So, if we measure that way, the occurrence of that event or the likelihood or the chances of that event to occur, then that is what we shall refer to as probability. And you may find that in life activities we may have several of them. One may be that, like a candidate in a school may be likely to know her or his chances of passing exam, as well as a farmer who has a cow of which has given birth to 5 times. And within these 5 times, only one heifer and 4 bulls are being given birth. So the farmer may want to know if the cow will give birth to the 6th time, how or the probability of that cow giving birth to a heifer, what will it be? So in that case, you will find out that if in the first 5 past record we are having 5 of the cow had given 5, let's just call child, but this is for a cow. So one is a bull and another one is actually 5 young ones. And under these 5 young ones, 4 were bulls and 1 was a heifer. Then the farmer actually is likely or interested to know if the cow is to give birth to a 6th young one, what's the chances of that 6th young one to be a heifer? So in that case, you will find out that to find that 6th to be a heifer, then you will take, if the total of that young ones is 5, and only one heifer within that past time is only one heifer which was given birth to with the 4 bulls, then the chances of that cow to give birth to a heifer, it will be one heifer which has been given birth to that given period of time over the total number of young ones a cow gave birth to, which is 5. And if this one is now the probability of finding a heifer, and if it is for bulls, then you will find out that it has given birth to 4 bulls, and out of 4 bulls, a total of 5 young ones was delivered. So you will find that this is the probability or chances of that cow to give birth to a bull. So this is for a bull. If you determine this way, you will find out that the 6th, actually the chances of that cow giving birth to a 6th young one being a heifer, you will find is 1 over 5. And that chances of giving birth to a bull, it will be 4 over 5, as we can see here. The analytical measure of the chances of which the cow will give birth or any kind of probability you will have, then that is what we do refer to as probability. This is how it do happens. It may be involved even like 2 people, you may have one like A, another one B, who may agree that they want to play and toss a coin. And on that event of tossing a coin, one agrees that if the tail wins or the tail shows up, then B may be the one who will win. And if the head is tossed and shows up, then A will be the one who wins. So in that circumstance, each of them will be determined or likely to know the probability of him or her winning the game. So you will find for that case, the probability which will occur is that the tail and the head have equal chances of showing up, so they will have a probability of a half. That is what we are referring to as probability. We are going to use a coin and another coin. This is what we shall be using, and you will find in tossing a coin it has two sides. One, which is the front side, will be a head, and if you have this new coin, it will be looking like this. And for the old coins, we have a head of one of the presidency. And you will find if you toss the coin, it may also have the back part of it, and the back is what we call the coin, the tail actually of the coin. So if you toss and it gives this back side, then it will be the tail. So let's see how we may use it in our experimental probability to help us evaluate what we are doing. Now we are going to study about experimental probability. And under this we shall be guided by tossing a fair coin. So as I said, a coin has two faces. One of the face is a head and another one is regarded as a tail. So if you find for a new coin we have a face like this, then that is what we do refer to as a head, and the other one has the face of presidency. That is still the head for the old coin. And if you view the back side of the coin, you will find that the back side has lion shield. So that lion shield is what we refer to as a tail. So we shall go on and use this coin in evaluating our experimental probability here. So we shall view in a case where somebody tossed a single coin 100 times. Using this single coin, and tossing a coin is just throwing it up and then you allow it to rest and see which side does the coin lie on, or the face that will show up. So tossing a coin is doing this, and then you view the side, or you make it rotate in air and then it comes back settling that way, and then you view the side which the coin faces face upward. So that is how we do toss a coin. So we shall consider a coin which was a fair coin which was tossed 100 times, and the number of heads which show up and also the tails which show up during that experiment. So you will find out that if somebody tossed a coin, tossed a fair coin for 100 times actually, you will find that within that 100 times, her head was shown 54 times and a tail was shown 46 times. So this implies that the number of heads that shows up were more than those of a tail. So if the person wanted to know, after tossing the coin for 101 times, what is the probability of that person getting a head or a tail? So you will find out that the total number of events that occurred is only one, is tossing a coin, but the coin was tossed 100 times. So you will find the number of times that the coin was tossed, we have said is 100 times. That is the total number of the occurrence. Then 54 out of 100, 54 were, or 54 times the coin shows a head. So you will find that the probability of getting a head will be that number of head which shows up over the total number of tossing that coin, which is 100 times. So if you do that, you will get the probability of tossing a coin and finding a head showing up. So that is how it will be. So if you take this one, you are going to have 27/50. Now 27/50 is the probability of getting a head. This is the probability of getting a head showing up. So if you want the probability of getting a tail, then you will take the number of times that tail shows up within that tossing time, and you will find it is 46 times. So this is 46 times for the number of tails, and the total number of occurrences were 100. So you will divide by 100 and find what is the probability of getting a tail showing up if you toss a coin 100 times. You will find this one is going to give you 23 out of 50. So 23 out of 50 is the probability of finding, this is the probability of finding a coin showing up a tail. So this is the probability of that tail showing up. And this one are abbreviated by, if you want to find the probability of a coin showing up a head, they are abbreviated by, you start by capital letter P to indicate that you are finding the probability. Then in bracket you place whatever you are investigating, that is the head. So probability of finding a head, now you can write this one as 27 over 50. And that of a coin tail will be, probability of a tail showing up will be equal to 23 over 50. Now that is how we do write the probability. From what we have done here, we shall find out that for that 101, determining either the chances of getting a head or a tail will be that for a head will be 27 over 50 and that of a tail will be 23 over 50. Whatever we have done here is the probability, but we have determined it basing on the past 100 times. So it is based on the past result or past experience of what we have done. So it is the past experience or past experiment which have been done. Hence, whatever we are referring to is what we are referring to experimental probability, because of the tossing has taken many times and by observation. So that is experimental probability. From what we have done here, you should note that in every toss, whatever you will get, or in every toss, that is what we do refer to as trial. So, if a fair coin is tossed once, then that is what we refer to as a trial. Trial is written as that way. So this one is, for this case, it will be for every toss. Toss of, as I will show you, throwing the coin up or in order to obtain the chances of it becoming a head or a tail. And then, whatever you are expecting to occur or the outcome of that toss, actually the result of the toss, then it is what we do refer to as outcome. So you will find these are the terms which are used in probability. Trial, outcome, that is what we shall be referring to. The chances of it becoming a head or a tail is what I'm referring to as outcome. So having the two, you will have to understand whatever you will be doing in whatever you will be understanding. So you will find out that whatever observed or done together with the recorded observation here is now our experiment. So if you observe and you record what you find is what we shall refer to as experiment. So in general, we can say that in order to find experimental probability, then it will be equal to like finding or taking the total number of favored outcomes. For our case, we had favored outcomes for head 54 and that of tail 46. So it will be number of favored outcomes over total number of trials, or the total number of trials or tossing. So you will find out that in order to find that, that is how what we usually do. So we are going to see an example. And in this example, we shall say that we have from the past records, out of the 10 matches a school football team has played, it has won 7. How many possible games might the school win in 30 matches? Let's see how we may give solution to that. So we were informed that a school had already played 10 games. And out of these 10 games, that school had won 7. So this is an experimental probability where an experiment was done by playing the game. So the event or the trial was the match which the school was playing, or that game which the school was playing. And then whatever was the result is what we refer to as the outcome. Now, winning here is what we shall refer to as outcome, and the 10 games played is our total trials. So for this case, in order to find the probability of winning, so I shall write probability of winning for that school winning that game. It will be the total number of wins the school obtained in that game, so that is 7, over the total number of games played, which we shall refer to as trials. So it will be over 10, and we are finding that the probability of winning will be 7 over 10, meaning that of either drawing or losing, it will be equal, and it will be 3 over 10 if we were told. But here we were told only the probability of winning. So we shall have that way. But we have been told to calculate the number, or to find out the number of matches this school is capable of winning if it plays 30 matches. So you will find out that if in 10 matches alone, the school has a probability of winning 7 over 10. What about 30 matches? So you will come and say, in 30 matches you will find it is capable of winning 7 over 10 multiplied by 30 matches. And you will find this one is going to give you 21 matches. So it will win 21 games. Matches is the same as games. So you will find in 30 games that the school will play, it is capable of winning 21 games. So that is what we do refer to as experimental probability. And I believe you have understood how it was practiced out, because you have to base on the past experience whatever occurred, and then from there you make a judgment on what is likely to happen based on that past experience. You can use the knowledge to evaluate out any kind of probability which involve experiment, and thus working out experimental probability in any problems concerning them. Let's view or work out ranges of probability measure, and under here we may observe that if you have worked out some of the given probability and you find some of them have much more greater chances of occurring, so the more the chances of occurring, then the greater the probability of that. So if the probability or more probability of, or let's just say the greater the probability of a given event to occur, the more it is likely to occur. That is our fact. And another one is that you will find some of the events are just certain to happen, in that it is impossible for them not to happen. Such events have a probability of, let's say for example, event A, we are just certain that event A must happen. If that is the case, then this event A, its probability of happening must be equal to 1. And in case another event, we are just certain that that event is impossible. It cannot happen. So if that is the case, then the probability of that event occurring, we shall have it as 0, because it is impossible for that event to occur. And an example with this is that you may have like days of the week. So if today is, for example, Monday, we are certain that tomorrow must be Tuesday and not any other day of the week. The chances of tomorrow being any other day of the week is 0. So the probability of tomorrow being any other of the day, it will be 0. But because we are certain that tomorrow must be on Tuesday, if today is Monday, then the probability of tomorrow being Tuesday is equal to 1. So that is what we are referring to as if we say, if one event is certain to happen, then the probability is 1, and if it is impossible or uncertain to happen, is equal to 0. So that is one of them. And another one, we can find that in any given probability, you will always find that it is always lying within an interval of, let's say, for example, it's a probability of A. So you will find this probability of A will always lie within the range of 0 and 1. It can either be 0 or be 1. This here, whatever you are seeing, is what we now refer to as range of probability. This is what we refer to as range of probability. So from there, you will find out that the given ranges or the given probability may be expressed in terms of percentage. You may find them in terms of fractions, and you may also even find them in terms of decimals. So it depends which best method suits you. So you can either express them in percentage, fractions, or decimal. For the case of heifer, the obtaining of heifer, or for the farmer, you will find that the probability was expressed in terms of fraction, whereby that of to obtain the bull, we found out was 4/5, and that of obtaining a heifer in a fifth delivery was to be 1/5. So this one was a probability of obtaining a heifer, and this one was a probability of obtaining a bull. So that is how we did do it, and that is how we found. But these still two probabilities can be expressed in percentage by multiplying by 100, and you express them in percentage, or you divide them completely and give the answer in decimal. You can still do that. So whatever we have seen here, especially this, is what we do refer to as the range of probability measure. And as we shall be working out, we shall find out that our workings and likely of events to happen will be lying within 0 and 1. So let's go on and find much more about probability. Let's now view probability space, and we will find that probability space refers to the list of the possible outcomes that may occur within an event which has just been happening. So you will find out that this one here, what we refer to probability space, it will be also be referring to as, may also be called sample space, because it's within the outcomes of a given event occurs. So it may be also referred to as possibility space. Possibility space. So for the case of a coin, in tossing a coin, let's say once, you will find out that the probability space in tossing a coin will be 2, because if you toss a coin once, if it is once, the physical nature of that coin is that the coin has equal chances of either a head or a tail occurring. So you will find out that this one will have 2 of actually the probability space. So the probability space here is going to be 2. And if you have two coins being tossed together, two coins meaning that you have one coin in one part and another one like this. Then you toss them together, like you throw them, and then you find out after they fall what is the probability or the sample space of that. You will find that we are likely to have 4 sample space. For example, let's say this is faces. Here, for the first coin, let it be on this side, first coin. Then for the next, second coin be on this face and this side. So you will find out that for first coin, the probability is that it will either give us a head, or a tail. And for the second coin, the same appears. It will either give a head or a tail. But if we toss them together, you will find that if you toss them together, the probability will be that you will either get a head and the other coin also shows a head, or if the first coin shows a head, the other one may show a tail in that case. Or the other way may happen. If the first coin shows a tail, the second coin may show a head, such that you will have tail head. And if the first coin shows a tail, the second coin may show a tail also. So you will have tail. Whatever we are having here as head, what we are having as head, tail, head, and tail. This is what we do refer to as sample space. This is our working space. It is now our sample space here. So that is what we do refer to as probability space or sample space or any given. So it may be even for the dice being tossed or for any other kind of event which occurs, even football games which are being played. Whatever the result you will have or the outcomes is what we will be referring to as the sample space. That is the list of the possible outcomes which occurs in a given event. Let's see how we can find a theoretical probability. And under here we shall answer it like, this is the probability obtained in a case where we don't require the past experience in whatever we are finding. For example, it may be that for a coin, we know the physical nature of a coin is that the head and tail have equal chances of occurring. That is a half. So you will find out that for that case, if you toss two coins together, the probability is that you may either have a head or a tail, but if you toss them together, you are going to have either two heads together, that is both the coins showing up heads, or showing head and a tail, or two coins one showing head, tail, and another one showing head, and the other one may be showing tail and another one tail. In case this is the first coin and this one is second coin, if you toss them together, this is actually what you will find as your probability sample space, and this is after either doing as an experiment or you may just give it theoretically, because it doesn't require an experiment, because the physical nature of a coin is that you are determined that it is either a coin will show up a head or show up a tail, so meaning they have equal chances of occurring. So that is how we'll find out. So meaning the probability space there, we are going to have a head, and also head, tail. We are going to have tail, head, and have also tail. So that is what we shall have as a sample space for that tossing two coins together. But if you are asked to give out the probability of obtaining a head and a head, if the toss were tossed together. So if the coins were tossed together, you will find out that for a head and head we are having 2. So it will be 1. Here is 1. We're having another space 1, another one 1. So the total of them are 4. So it will be 1/4. Of obtaining a head, 2 heads actually is 1/4. This one is probability of obtaining 2 heads. And obtaining a head and a tail may be in either way. So you will find it is equal to, we have 2 heads. We're having a head and tail which are 2. So it will be 2 of them. But the total sample space is 4. So meaning that we are going to have a half. That is for obtaining a head and a tail. And if it is a tail and a tail only, or 2 tails, you will have that you are going to have one of them out of the sample space, which is 4. So we are going to get, to obtain 2 tails showing up is 1/4. 2 heads showing up is only 1/4. That is the probability. But tail and head showing up, we shall have it as a half. So this one here, we have done it by experiment, but there is a way which we can do this one using a theoretical way, and that is, we know that the theoretical probability of obtaining the physical nature of a coin is that a head has equal chances of showing up with a tail. So meaning that the chances of finding a head in a single toss will be a half, and that of showing a tail in a single toss is equal to a half. So if you are being asked to find 2 heads showing up together, so a head and a head, you will have a half multiplied by a half, and you will get the probability of a coin showing up 2 heads will be equal to 1/4. That is how it shows up. And if it is 2 tails, it is a half multiplied by a half, then you will get 1/4, or you add up together, so you will get is a 1/4. That is how it happen. So if you multiply, you are going to get that. The same applies to that of a head and a tail. So that probability which is found without requiring the past experience, as we can see here, is what we do refer to as theoretical probability. And an example we can tackle is a dice being thrown up once or tossed once. If you have a dice and you toss it, then the probability is that you will have one of the either sides. Remember, a dice is a solid figure which is a cuboid in nature or a cubic in nature. It may appear to look like a Royco cube if you have ever seen one. And it has 6 faces. In case these 6 faces are numbered number 1 up to 6, you will find out that if you toss only first toss, you will find that the probability or the sample space you will have 6 of them, and the probability will be in different cases. So you may be either the dice may show up the first numbered 1, or first numbered 2, or first numbered 3, 4, 5, and 6. These are the faces or the numbers which have been indicated on each face, and you will find out if you toss that die, it is capable of giving either 1 or 2 or even 6 showing up. So if you toss once, this is what will occur. But let's find the probability that a face number 1 will show up. If a face number 1 will show up, we shall find out that in tossing once, you will have only one face showing up within the possible outcome which may occur, and that will be equal to 1, which is this one, only one outcome of 1, over the total outcome which we expect to occur, and that is 6. So you will find the probability that that dice may show that first numbered 1 is 1/6, and it will be throughout because it is the first toss. Even the probability of showing 2 will be equal to 1/6 because number 2 will be shown only once in a single toss. So that is how we do calculate. But if you have been asked a probability of showing even number, the probability of showing even number, then it will be different. Here we shall take the probability of showing even number. We know it will be probability of, it's the same as being as the probability of 2 showing up first 2, 4, and 6. Those are the even numbers we have there. So you will find out there that way. So in that case, so we shall find out that the probability of getting only number 2, it is 1/6. So in case to get the probability of finding an even number, we shall add all the probability. So we are going to add that one, and we shall find, we are going to have 1/6 plus 1/6 for that of number 4 showing once, and 1/6 for number 6 showing once. That is the first number 6. So you will have as 3/6, and this one is going to give you a half. So you can use that way out to calculate given probability, which doesn't require past experience. So with that, we have seen what is theoretical probability, and we are going to see an example from exercise 13.2, number 5. That is 2 dice are tossed together. What is the probability that the sum of the numbers showing on their upper face is either 3, 5, and 8? So let's see how we can calculate that. Here we have been issued with the 2 dice, and we know each dice has 6 faces. 6 faces. So if we number these 6 faces in terms of numbers, we may give it from number 1 up to 6. So meaning that if there are 2 dice, then each dice will have 6 numbered faces, and in that case we shall construct our probability space such that we may have dice here. Then we have first dice here, and here we have a second dice. So that this one is numbered 1, 2, 3, 4, 5, and 6. And the other one is 1, 2, 3. That is what we shall obtain as. So whatever I haven't filled here is what we refer to as our probability space or possibility space or sample space. So we need to fill out and find out what we shall be obtaining in that sample space. So we are going to have, we have been told it is a sum of 2. What is the possibility that the sum of the numbers showing on their faces, upper face, is 3? So in this case, we shall do this. We want to find the sum. If in case you throw the first dice, or you throw them together once, it is possible that if the first dice shows 1, the second may show 1. So meaning the total sum will be 2. And the other one, if shows 2, then this one 1, you will have 3. Here 4, 5, 6, and 7, if that is the case. And if the second die shows number 2, the first may either show 1, meaning the total or the sum may be 3. And if it still shows 2, the other one may show number 2 or face 2. And if you sum, you will find 4 as you continue will be in that category. So that one continues that way. If it shows, the second one shows 3, the first shows 1. If you sum, you are going to get 5. No. If 3, 1, you will get 4. And then if it's this second shows 3 and the first shows 2, you will find the sum will be equal to 5. As you move on, will be in that case. So you will find out that the sum in summing them in respective showing up, it will be as we shall find out in this table here. That is what we find out. So whatever I have written in black is what we refer to as sample space. So from here, we are finding that we are having approximate of 36 sample space from only 2 dice tossed together. So thrown together or tossed together is the same thing. So we have that. So we were asked to calculate or to find out the probability that a number showing on their faces 3, if the sum is either 3, so we want to find out the probability that the sum of the number showing or the sum of the faces will be equal to 3 after tossing 2 dice together. So we shall find we are having only 1, 2 threes showing up. So if it's 2 threes, then we shall say we're having 2 of them, but they will be out of the total number of that given, total number of the sample space. And our sample space here is equal to 36. If you count out, you are going to get 36 of them. So if you do that, you will now find out that this one is going to give you 1 over 18. So the probability of that one showing the sums of the faces showing 3 is 1 over 18. Let's see if the sum is showing 5. You will find that for 5, we are going to have, here is 1, 2, 3, 4. So there are only 4 as we can see. So if that is the case, we are having 4, then we shall take 4 over the total number of sample space, and the sample space here we are having is 36. So the favored outcomes are 4 and the total number of trials we are having 36. So we shall have 4 over 36, you will get is 1 over 9. So that is what we shall have as the probability of obtaining the sum of the faces showing 5. And then another one is to find the sum of the faces showing 8. So that of 8 will be equal to, now you count the 8, and the 8 is here, 1, 2, 3, 4, 5. 8, there are 5 in number, so you will find that it will be equal to 5 out of the total trial or the total sample space, and that is 36. So you will find this is our probability of showing 8. And if it is probability that the total number will show up number 7, then you can calculate that from there. And I want you also to calculate the probability of the number showing up 12. The faces, the probability that the sum of the faces will be 12, and that of 10. That one, I want you to calculate and give out what will you find as the answer of that given probability. So I have left these 3 for you. Now let's go on and find combined events, and under combined events we are going to start with the mutual exclusive events. And under mutual exclusive events, we shall find out that these are events in which if one occurs, will affect the occurrence of the other, meaning that if one occurs, the other one will not occur because it depends on the other one. So they are actually dependent events. So mutually exclusive events, they depend on each other in order to occur. So we can say the occurrence of one event will affect the occurrence of the other one. And this may apply in case of where you have like a coin being tossed. You will find if you toss a coin once, one coin once, you will find out that the chances are that you will either get a head or a tail. You can't get both of them once if you have one coin. So that event we also refer to as mutual exclusive. The same applies to tossing dice. If you have a dice and you toss it, if the faces have been numbered 1 to 6, you will find that there is only one chance that one of the faces will show up. Not all of the faces will show up. So that is how we do determine mutual exclusive events. So in case you have a fair coin, a fair coin, and you toss it once, the probability of getting either a head or a tail may be given by, for example, let's say probability of getting a head or a tail, or just let write in full. The probability of getting a head or a tail, we shall say, is the same as probability of head or tail is given by, if you hear head or a tail, it's like you are being told to sum up the two of them. So the probability of getting a head or a tail in a single toss will be equal to 1. Why? The probability of getting a head in a coin tossed once, you'll find is a half, and also getting a tail is a half. So if you add them together, you're going to get 1. Here, the term or, as we have seen being used here, is usually referred to as addition rule in probability. So in combined mutual exclusive events, or will be used to imply addition of given probability. So we shall see an example here and find out what we have in different ways. Now, here we have been told 2 dice are thrown together. Find the probability of getting a sum of 8 or 3, 3 or less, at most 7, greater than 9, at least 6. So here, what we shall do here, we are going to take the 2 dice. Here I don't have them, but I remember I told you a dice have an appearance of a Reiko cube. If you take the Reiko cube, you number each face as 1 up to 6, then it will resemble to the faces of a dice. So here we are going to have that sample space of dice, and we shall say it will be equal to Now let's determine the sample spaces of these dice. Here we are having 2 dice. The first dice is up, and the second one is on this side. The number here represents the number of faces will show up in a single dice. Will have like 1, 2, 3, 4, up to this number. So these numbers which are indicated on dice row and column are the faces of the dice which is likely to show up. So let's find the sum in case the faces show up in respective ways. Let's find the sum of those faces. If the second die shows face 1, then the first shows 1, we shall find a sum of 2, and that one will continue as we have here. The same apply to this. If the second die shows face 2 and the first one shows face 1, the sum will be 3, and the other one shows 2, it will be 4, here 5, 6. As we continue, you will find out filling the table. Please help me fill the table. If this one is 3 and this one shows 1, let's go together and fill. So we are going to have those faces being summed up to those given numbers. So that's what we shall have. As for this number 12 here is first dice showing face 6, and actually first dice showing face 6 and the second one showing face 6. So we shall find a sum of 12. From there, we can now find, using our given exercise there, it was to find the probability that it will either the sum of the faces showing up will be equal to 8 or 3. So we shall have the sample space we are having 36. The number of trees which will show up we are having 1, 2. So there are 2 for 3. There are 2. Or we can say if you have been told to find the probability of either the sum showing the faces showing up is 8 and the sum of showing up is of the faces is 3, then it's the same as being asked the probability of the sum of the faces being 8, or means you add that of the sum of the faces showing 3. So in that case we are going to have that of 8 we shall have as 1, 2, 3, 4, 5. So there are 5, and we have a total of sample space as 36. So we shall have 36, and then we add to that of 3, and that of 3 we found is 2, so it will be 2 over 36. And if you simplify this one further, it's going to give you 1 over 18. So it's the same as writing 1 over 18. So if you add that one, you are going to have 7 over 36. So that is what we shall have. The probability of finding 8 or 3 we have found is 7 over 36. And we are going to find the probability of the sum of the faces showing up is either 3 or less. So either 3 or less, we shall identify here the sum of the faces showing up is either 3 or less of that 3. So if that is the case, we shall find the probability of is the same as finding the probability of 3 of the sum of the faces showing up is 3 or less. So we shall add to those of which are less, and we have only 1 of 2. So probability of 2. That is how we do find out. So if that is the case, we shall now come up with probability of 3. We are having number 3 being twice, or 3, the sum showing 3 will be twice, so it's 2 over 36, and that is 1 over 18. Plus that of 2 is 1 over 36. And if you add up this one, they are going to give you 3 over 36. And that one is the same as writing 1 over 12. So the probability of the sum of the faces showing up is 3 or less will be equal to 1 over 12. So that's how we do find out. Let's go on and find out the probability that it will show up at most 7. The probability that the sum of the faces will show up at most 7, they mean that we are going to find 7 included, but we are finding 7 and less. At most means the greatest you can find, the sum which you can find as greatest is 7. But we need to find 7 and less. So we shall find out 7, or just let's write at most 7. At most 7. So this one is the same as probability of 7 or less. So if it's 7 or less, it's the same as finding the probability of that 7. We have another one of the faces showing 6, so we shall add that of face showing 6. We have face showing 5. Another one is face showing 4, 3, and we have that of 2. So that is what we shall find. So we are going to add all that, and whatever I have done there is the probability that the face which we show, the sum of the faces showing up will be either 7 or less, which means at most 7. So that is what we shall have. So we shall start with that of showing 7, and if it is 7, we shall have those showing number 7, we are going to have as This one is 1, 2, 3, 4, 5, 6. There are 6 in number, so it will be 6 over 36. We add to that showing number 6, and that of number 6 will be 1, 2, 3, 4, 5. So we are having 5 of them. So there are 5 over 36. We shall add to that of 5, and that of 5 is 1, 2, 3, 4. There are 4 in number, so we are going to add 4 over 36. And we shall add to that of 4, and that of 4, you can help me, there are 3. So it's 3 over 36. Plus that of 2, and 2 we just found 1. That of 4, 3 over 36, and that of 3, we are having 2 of them, so 2 over 36, and then we add to that of 2, and that was 1 over 36. So we add that of 1. So we shall find, let's see what we find out as the probability of that, at most 7 or less, or 7 or less. We are finding the total is 21 over 36, and this one is the same as 7 over 12. So if you work out, you are going to get the probability that the sum of the faces will showing up will be either at most 7 or 7 or less will be equal to 7 over 12. And we have worked out, you have seen how I have worked out, and that is how we do that. So we have another one, at least 6. If you have been asked at least 6, that one I'll give you. So at least 6 is it does mean that the sum of the faces showing up, it is either 6 or more. You should not exceed 6 and below. It is 6 and more. So it is either 6, 7, 8, 9, 10, 11, or 12. So that one, I need you to help me find it. Now I would like you to find the probability that the sum of the faces showing up if 2 dice are tossed together are greater than 9, at least 6, or even number. Even number, you understand, is a number which is divisible by 2. If that is the case, you will find out from this what I have shown you. Find out the probability of that. At least 6 I have already explained, the same to greater than 9. Under mutual exclusive events, you will find out it applies to different kinds and forms of given events in our life activities, that is in our daily activities. You will find out you may be given some balls in bag, and you choose, maybe there are given number like 5 red balls, and or maybe it may be marbles. You may be given the number of balls which may be of different color. In color may be different. So you may have others in green, others white, others black, or even blue. So you may be told you are picking randomly from the bag, and you identify the probability of picking a given ball from that bag, either with the replacement or without replacement. Without replacement, you just subtract 1. With the replacement, you maintain the number of the total balls. So that is how we do work out. We shall see in more as we go on working out. So you may use that information to work out mutually exclusive events, and you will find out in mutually exclusive events, we say mostly they use the term find the probability of a given event or other events. So that or is used as addition rule in probability, and mostly used under mutual exclusive events. So let's go on and find another combined event, and that is for independent events. And under independent events, we shall find out that this one here, if we find the probability of independent event, you will find out that is that the likelihood or the chances of one event happening, say it like event A, does not influence or affect the occurrence of another event, which may be event B. So, meaning that they occur at the same time, and since they doesn't influence each other, both will give us the positive result of their respective occurrence or chances. So you will find out that in independence event we may have, like you have a coin and a dice being tossed together. So the occurrence or the likelihood of a coin showing up a head or a tail does not influence the dice showing up either face 6 or one of its faces. So you will find out that you will have, for a coin, a fair coin being tossed, you will have either a head or a tail. And for a dice, you will have either face numbered 1, 2, 3, 4, 5, or 6. So those are the faces for the dice. If you number them, you will have that one. And a coin will be head or a tail. So the probability of the two occurring together will be obtained by taking the product of the individual occurrence. For example, for this case here, you will find out that the probability of the two occurring together, you will find out that is the probability of a coin and, let's just say, a coin and a dice occurring together is the probability of that coin multiplied by the probability of a dice occurring. So you will find that's how we find. So and in this case is used as multiplication rule in probability. So it will be a multiplication rule. So if you find you have been told and, know that is a multiplication rule. If it is or we saw for mutually exclusive events, it was addition rule in probability. So we are having that way. For this case, if you are being asked, for example, find the probability that the occurrence may be a head and a number 1 showing up if a dice and a coin are tossed once, then you will find that we are going to have a sample space, and under that sample space, you will have a head and a coin occurring only once, so it will be 1h over the total sample space. Let's see how we shall find out that one. So we shall have, if a dice and a coin are tossed together, we are going to have these faces. For the dice showing up, we shall have either of the face showing up, which we say is mutually exclusive events. And if we combine them with another mutually exclusive event, which is that of a coin, then these ones here becomes independent events because occurrence of each one of them does not affect the other. So we shall have this way, and the sum of them occurring, or the chances of them occurring together is the product of the probability between them. So we shall have, for here it is T2. This is the face of the dice and that of coin showing up, occurring together. So we shall find that way. So we are going to have, in that case, that as we have there. So we shall find out that this is what we have. But if you are being asked to find out the chances of a coin and a dice occurring together, and a dice occurring together showing 1 and a head, or a head and 1, it will be the probability of a head and 1. So a probability of a head and 1, you will find for this case will be equal to, if it's a head, we know it's a half, and 1 we have 1, it will be 1 over 6 because only one part of that will show 6. So you will find on working out you are going to have 1 over 12. Probability of getting a head in a coin we saw is a half, so that is how we do find out. But you can still find it through working out in experimental, and you do say that it will be a head and 1 is only this. So it will be 1 out of the total sample space we have in here is 12. If you count all of this one is 12, which is the same as calculating. So we can find out that the probability of two independent events occurring together is the product of the individual probability of each event, as we have found out. So we shall see some of the examples here. Let's continue with our example. We are going to see an example on independent events. And here I'm going to tackle an example including the picking of balls in a given bag. So I have a question regarding that statement. That is, a bag contains 8 black balls and 5 white balls. If 2 balls are picked or drawn from the bag, one at a time, find the probability of picking a black ball and white ball with replacement and without replacement. We shall start with the without replacement. Under without replacement here, we shall find out that the first thing to identify or to note is to identify the total number of balls in that bag. And we shall find we have 8 black balls and we also have 5 white balls. So if we add them together, we are going to find 13 balls present in the bag. So meaning that if we are picking a black and white ball in that order, we first pick a black ball followed by a white ball, then it means the probability of picking will be determined by that. Let's now find the probability of picking black ball followed by white ball. And if that is the case, it's like finding the probability of black and white. So in that case, we are going to find the probability of picking black ball from 13 balls. So it will be, we have a total of 8 black balls and the total number of balls in that bag are 13. So the probability of picking one ball which is black will be the total number of balls which are black, that is 8, over the total number of balls in the bag, which is 13. So we shall multiply by the probability of picking white ball. And since we have 5 white balls in the bag, and the number of balls already we have picked 1, which was black, so meaning the total number of balls in the bag has reduced by 1 to become 12. So the probability of picking white ball from that bag will be equal to 5 over 12. And if you do that, you are going to get, this one is going to give you 10 over 39. But remember one thing, if you picked the first ball as black, followed by white, you can still pick the first ball as white, followed by black, without replacement. So meaning that we can also pick probability. So we are going to find the probability of white ball followed by black. So this one is the same as finding the probability of white and black ball. So if that is the case, we are going to have the probability of picking white ball. If we have a total number of 13 balls, will be equal to the total number of balls or favored outcomes of white balls is 5 over the total number of balls, that is 13. So we shall multiply because of and there, and we shall multiply by the total number of balls for picking a black one, which is 8. But remember, since you have picked one white ball, the total number of balls in the basket or the bag has reduced by 1, so it will become 12. If that is the case, we are still going to have, that one is going to give us 10 over 39. So you're going to have 10 over 39. And remember, the event here of picking the first pick and then the second pick is independent event, because if you picked the first ball, next ball does not, picking of the second ball does not influence the first ball, or the picking of the first ball does not influence the picking of the second ball. That's why it is independent event. But after picking, where you have picked white followed by black, or black followed by white, it is mutual exclusive event, because this one or that one will give us a probability. So meaning that the probability of picking white, actually let's start with black and white, or we have probability of picking white and black is a mutual exclusive event, because if you pick the first one, this method, you can also pick up this one. So they are mutually exclusive, that one if occurs, the other one will not occur. So if you use this one will not occur. But if you use this one will not occur. So that means we are either taking this or the other one. So that means we are going to take probability is the same as probability of black and white plus probability of picking white and black. So if that is the case, we are going to have probability of black and white we got is 10 over 39. So we shall have 10 over 39. We add to that of white and black will give us 10 over 39 again. And this one is going to give us 20 over 39. So that is the probability of either picking black ball followed by white, or black ball followed by, actually this one should be white ball followed by black. So if you pick in that case, you will find it is 20 over 39. That is without replacement. Now let's consider a case where we are picking with the replacement. Let's consider a case where we are picking with the replacement. Since we know the total number of balls in the bag are 13 balls, and number of black balls we have in that bag is 8, and that of white we are having 5 balls. So we can still find out the probability of picking a white ball and a black with replacement. So we shall start by picking, or the probability of picking a white ball followed by a black ball. So it will be probability of white and black. So that one will be equal to, we are going to take the probability of picking a white ball from that bag will be 5 over 13, as you have already seen. But we shall multiply by, because of the and is multiplication rule in this independent event, so we shall multiply by the probability of picking black ball. And since we have said we are replacing, after picking the ball, you replace it back into the bag, then it means that the probability of picking a black ball will be now 8 over 13. So if that one is the case, we are going to have here 40 over 169. So the same applies. After picking a white ball followed by black, you can also find the probability of picking black ball followed by white. So meaning it will be black and white. And if that one is the case, is finding the probability of black multiplied by probability of white. So we are going to have probability of that will be, probability of picking black, the first black, will be 8 over 13. But since we have said with the replacement, then it means the ball which you have picked, you take it back into the bag to make the remaining number, which was 12 now, to be 13. So meaning, now for picking white will be also 5 over 13. And that one is going to give you 40 over 169. Now, the independent of picking a black ball and white ball is actually the probability of picking is independent event. So the occurrence is independent because the first picking of the ball does not influence the second picking of that ball. Thereby, you can either pick a white ball or a black ball in the first event, and in the second event you can either pick a white ball or a black ball. But in two events, you can either pick one and other, that is black and white, or white and black. So the picking there after independent event, what you have here is what we call mutual exclusive event. It is either this method which will occur or the other method which we have here. So meaning that after finding independent event, you will have that it is either probability of black and white which will occur or that of probability of white and black. So meaning that if one of the methods occurs, the other one will not occur. And if the other occurs, the other one will be prevented from occurring. So this is what we shall have. So we shall find that one, and this one is the same as finding the probability of B or black and white plus probability of white and black. So on doing that, we are going to have 40 over 169 plus 40 over 169, and this one is going to give us 80 over 169. Now this is the probability of picking a black and white ball without replacement considered in two dimensional, in all dimensional, that is in one way and another way, as we can see. So the same applies in case you have been given different kinds of probability, and remember, in case you have some events, for example, one of the events occurrence, like let's say PA is equal to, let's say the probability of event A occurring is P of A. So meaning that if that is the probability of event A occurring, you can also find, if you have been given some of them, that the probability of event A not occurring is abbreviated by A prime. So this one may be referred to as probability of event A not occurring will now be equal to 1, which is the greatest measure of probability, since we saw the range of probability was between 0 and 1. So we shall find out that it will be that one minus that will occur. So if you do that, you will be finding the probability of event A not occurring is equal to 1 minus the probability of that event occurring. And in case you want to sum them together, we will find that if you take the probability of event A not occurring, you add it to probability of event A occurring, you will find you are going to have 1. So meaning that in case you work with probability, whatever answer you must get should not exceed 1, because the range of probability is within the range of 0 and 1. If you find 2, then whatever you have worked out is not probability. So that is how we do find out that one. Then next we are going to see tree diagram and see how we can enumerate some of the mathematical analysis of probability in that. So let's see how we shall work out using tree diagrams. Let's see tree diagrams, and we see the tree diagram is a way of enumerating probability space. So if that's the way, we shall find out that it is a way which is used in both enumerating of independent events and also mutual exclusive events. So in that case, we may see one of the independent event and also another one which may be mutual exclusive event, and even those of the two can be put together using tree diagram. A tree diagram will resemble a branch of a tree that is like this. So if you find something which may look like this, whereby you may have an occurrence like A there, probability of occurrence A, and this one be probability of occurrence B, such that it is divided, and here we will be given the probability of those occurrences. So what we shall have here, I'm going to test one example. We shall have one example, and that is tossing a coin. If we toss a coin, for example, 4 times, that is, a fair coin is tossed 4 times, find the probability of getting 4 tails, or something like 4 heads, at least 2 heads, 3 heads and a tail, at most 2 tails. So I'm going to use a probability tree diagram. So what we shall do in probability tree diagram, the first thing we know, a coin in tossing has equal chances of showing up a head and also a tail. So meaning in first toss, we shall have this branch here, and this one may be either a head or a tail. And if it is a head, I know the probability of getting that is a half, and probability of getting a tail is a half. That is first toss. Second toss may be here. And if I got a head, then in second toss, I will have either a head or another tail, and the probability remains a half, because I'm tossing the same coin the second time. But the probability of tossing the first coin for first toss, second toss is independent event. But you will find out that as you toss, as you move on, it will be mutual exclusive event. So for this one here, we are going also to have, if you've got a tail, you can either get a head or a tail in the second toss. In the third toss, after getting a head, you can either get a head again or a tail. If you got a tail at this kind, you can either get a head or a tail. The same applies to this head or a tail. The same to this head or a tail. So you will find out you are going to have that kind of tree diagram. That is the third. And then we have been told up to fourth toss. In fourth toss, after getting a head, you can either get another head or tail. The same applies to this. It is either head or a tail. This one also head or a tail. This also have head or tail. The same applies to this. Head or tail. Head or tail. And this one also has head or tail, the same to this, head or tail. So you will find, as you move on with the toss, you will find out that the sample spaces are increasing. Here we are having more of them than in third toss, second toss, and first toss. So whatever we are witnessing here is a sample space in each toss. So here in first toss, you will have 2 sample spaces. Second toss, you are going to have 4 of them. In third toss, you will have, as you see here, we have the double the number, so it is 8. In fourth toss is 16, as you can see. So the number of toss are going on as they increase. So meaning here, as you can see here, for that we are going to have 4 heads. That is head, 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 head. And for this one is going to give you head, 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 tail. This one is giving you head, head, tail, head. This one here, head, head, tail, tail. Here you are going to have head, tail, head, head. And this one, head. That one giving you head, tail, head, tail. Tail, head, tail.
So whatever I've written there are the sample spaces, and you can see they are resulting from whatever we have drawn using a tree diagram. Now here is what I refer to as a tree diagram, which is a branch. On the end of the branches we have the probabilities, actually the events occurring, and the probability may be given in that way. So each branch here represents a half. As we can see, it is a half to each other. So it's a half throughout. We shall be filling as we move on. So you will find out that way. So here we have been told, find the probability of getting 4 heads. 4 heads, we are having here, there are 4 heads, and it's only where they are represented as 4 heads. So the probability of getting 4 heads, that is head, as we can see here, then it will be equal to, you will take that one as, using a tree diagram, this is what you do. You will come here, get the first head is a half. As you move across, actually, as you move along a branch, as you can see, along a branch, we are multiplying. Moving along the branch, you multiply. That is independent event. But if you move across the branches, like you are moving from this branch to here, you will add. Either from this branch here to the other, you will add. From head to tail, you will add that way. As you move across the branches, then what you do, you will add. So that is addition is required. So let's see how we shall do. So for that case, we are going to use that method there, and we shall say as we move along the branches, we are going to multiply. So getting that of head, it will be a half multiplied by a half to get the second head, multiplied by a half to get the third, and then a half here to get the fourth head. So we are going to have a half multiplied by a half, by a half, by half. And you are going to get, that one is going to give you 16. So you are going to have 1 over 16. And as you can see here, we are having 16 sample spaces and only 4 heads are appearing once. So it is 1 over the total sample space, which is 16. So you can see from there. So meaning that whatever we are having here will lead us to find the correct value. So that is 1. As you move along, you are going to multiply. Then we have been told to calculate 4 tails. That one you will do. For 4 tails, I'll leave it for you. And here, 3 heads and 1 tail. So we are going to calculate 3 heads and 1 tail. For 3 heads and 1 tail, we can identify. Here we have 3 heads, 1 tail. That one is okay. Here we have 3 heads and 1 tail is okay. Here 2 tails, but that one we don't have. Here we have 3 heads and 1 tail. This one is okay. We are just identifying those events or in sample space where we are having 3 heads and 1 tail first. And then after that, we are going to have another 3 heads here and 1 tail. And another one is there any other present? No. So we have those containing 3 heads and 1 tail, we are having them as there are 4. So they are on different branches. So if they are on different branches, remember I told you, we do take addition if you move from one branches to another across the branches. But if it's along the branches, we multiply. So we shall find that probability of 3 heads and 1 tail, it will be this of 3 heads tail, or that of probability of head, tail, head, or probability of head, tail, head, or the probability of tail, head, head, head. So on doing that, you will be finding the probability of getting that given sample space that we have. So we shall have the probability of getting 3 heads as, so the probability now will become as, let's just say, equals to, now for getting the first one here, remember, since it is 1 out of the total sample space, or you can still work out by taking a half multiplied by a half multiplied by a half, actually this a half, multiplied by now a half here for getting 1 tail, and you will get that one is going to give you 1/16. That is, we have done with that. So OR means addition, so we shall add, and then for head, head, tail, head, we are going to have a half for the head, a half head again, a half for tail, and then a half for head. So we are going to have 4 halves. If you multiply them, you are going to get 1/16. We add to another one for head, tail, head, head. Head, tail, head, head. So we are going to have 1/16 again, which is a half throughout. Then we are going to have the last one, which is tail, which is a half, head, head, head. So we shall have it as 1/16. And if you add them together, you are going to get, if you add, that is mutually exclusive events. So meaning, if you move across the branches, you are undergoing mutually exclusive event. But if it's along the branches, that is independent events. So if we are going to add this, we are going to get 4/16, and this one is going to give you a quarter. So that is what we find with that, and that is how we work out mutually exclusive event using tree diagram, and also independent event the same way. So that's how it is worked out. So you will find out the probability of finding 3 tails and 1 head. I have shown you for 3 heads and 1 tail, and I want you to find 3 tails and 1 head. If you have been told to find at most 2 tails, it means you are going to find the probability where the most tails you can ever have is 2. So meaning it's 2 tails and 1 tail, where it will be this one of 3 head and 1 tail, and that where we have 2 tails. So you will take this here, head, head, tail, tail, head, tail, head, tail, and the others which I saw here, tail, tail, head, head. So there are also 3. 1, 2. Here we have another one, head, tail, tail, head. So there are 4. So meaning it will be a quarter plus a quarter, and you will find your answer to be a half. So that's what you will have there. So that's how you do find at least 2 heads. Then it means what you have most, the number of most heads you can ever have is 2. So you will do that and find out at least 2 heads. It means the least number of heads you can ever have is 2. So it is either 2, 3, 4 heads. So you will work out and find out what you will have. So that means it's an exercise for you to work out, and I will have another example here. Let's see another example containing the same. We have another example that the probability that a day is rainy is a quarter. So here, we have been told the probability that a day is rainy is a quarter. The probability that I carry an umbrella on a rainy day is 1/7. And that I carry an umbrella on a non-rainy day is 2/7. Find the probability that it will not be rainy and I carry an umbrella, and I shall carry an umbrella. So what we are going to do here, we are going to use the help of a tree diagram, and we shall start with, let the sample space of carrying or of raining be represented by R. So if you find somewhere R, Now that is the probability of raining. And not raining be represented by R naught. So we can say the probability of raining here now will be a quarter. So it is a quarter. Then it means that the probability of not raining, remember I told you, if you have the probability of raining as a quarter, then that of not raining will be equal to 1 minus that of raining, which is a quarter, and you will find here is 3 quarters. So on doing that, we are going to have there 3 quarters. And then we have been told the probability that I carry an umbrella on a rainy day is 1/7. So if it rains, the guy carries an umbrella. So we can represent that by U to represent carrying an umbrella, and U not carrying an umbrella. So if that is the case, we have been told the probability of carrying an umbrella is 1/7. So not carrying an umbrella will be 1 minus that, and we shall find it is 6/7. The statement continues, and the probability that he carries an umbrella on an rainy day is 2/7. So meaning, if it is an rainy day, for him to carry an umbrella is 2/7. So that is carrying an umbrella and not carrying. So not carrying will be 5/7. So that is how you represent the information on a tree diagram. And you have been asked, find the probability that it will not be rainy and I carry an umbrella. So it is not rainy. So this is for rainy. This one is not rainy, but I carry an umbrella. So we are going to use this one here. And remember what I told you. If you move from one tree branch to another and it's along it, then you are going to use formula of multiplication. That is independent event. So that is R naught U. And here we having R naught U naught. This is R U naught. And this one is R U. So meaning it's raining and I carry umbrella that way. So if we find the probability that it will not be rainy is here, so it will not be rain, but I carry an umbrella. So we are going to find this probability, and that one we are going to multiply that given probability there. It's 3/4 multiplied by 2/7, and if you do that, you will find out that he will have 3 out of 14. So the probability that it will not be rainy, but he carries an umbrella is 3/14. The next question, I shall carry an umbrella, means whether it is rainy or not rainy, that guy will carry an umbrella. So meaning that we are going to find the probability that he carries an umbrella. So meaning it can be either raining and carries an umbrella, or not raining but carries an umbrella. So if that is the case, we shall add the two probability because it's mutually exclusive event. So if it is raining and carries an umbrella, we shall find out, you will find out that that one is going to be raining and carries umbrella. You will find it a quarter multiplied by 1/7, and this one we shall add to not raining and carries an umbrella because we are moving from one tree branch to another one. So from here to here we shall add, but along we multiply. So we are going to have 3/14 because this one here we had already calculated there. So this one is going to give you 1/28 plus 3/14. So that is 7/28. So you're going to have 7/28. And if you cancel it out, you're going to have a quarter. So that is what you have as the probability of him carrying an umbrella either on a rainy day or not raining, it is a quarter. So that is how we do find. So I'll give you one and I'll direct you. That is from exercise 13.4. It's number 10. So we shall have, In a certain town, 15% of the people are bald-headed. If 4 people are chosen at random, find the probability that 2 are bald-headed, less than 3 are bald-headed, 3 are not bald-headed, and at least 2 are bald-headed. I will just help you to construct a tree diagram. The remaining you will do it and find out what I do mean by that. If in a certain town 15% are bald-headed, then it means it is 15 over 100. So 15% are bald-headed, meaning the remaining, or just say, we shall have a probability. We have selection. We have the first selection of a person, second, third, and fourth. Because 4 people, we are told 4 people were selected randomly. So will be, if 4 people are selected, know that if you are bald-headed, it means that is 15% of probability of getting that bald-headed is 15%. So means 15 over 100 if you change it to fraction. And this one will give you 3 over 20. 3 over 20. And if you are not bald-headed, let's say not bald-headed, you will find that you are 1 minus 15%, which will be 100 minus 15%, or 1 minus 3 over 20, and you will find this one is equal to 17 over 20, or 85%. So if you get that one, you are going to get that are the probabilities of getting a person not bald-headed or bald-headed. So let's say, let B represent those people who are bald-headed, and B not, B prime, represent those who are not bald-headed. So with that, I will help you to construct that tree diagram. And under this tree diagram, we shall start with the first selection. And we know for first selection or first person, you will find that you are going to have, for first, you will either have a person who is bald-headed or not bald-headed. And if it's bald-headed, note the selection is 3 over 20 or 15%. And this one will be 17 over 20, or you will have 85%. Then if that person is not bald-headed, or if that person is bald-headed, the second selection can be either you will find a person who is either bald-headed again or not bald-headed. And if you find the initial was not bald-headed, you can find another person who is either bald-headed or not bald-headed. So the selection remains the same. The probability of selecting, that is 17 over 20 and 3 over 20, 3 over 20 and 17 over 20. So the same applies for the third person, that is third selection. What we are going to do, and here you will find that the selection will always remain with the same probability, and this one will be my fourth selection, that is the fourth selection. So that's how you will find out the probability of given that with the tree diagram. So you will find for the first one is going to give you bald, and then those are bald-headed. And this one you're going to have bald, not bald-headed. This one will give you bald, not bald-headed, but bald, the last one. And this one, so that's what you're going to have as sample space. And there are actually 16 sample spaces. So we are going to have them as given there. So these ones are the given sample spaces, and from there you need to calculate 2 people are bald-headed. So if 2 people are bald-headed and if 4 people are selected or chosen, then you will come here and find out those sample spaces with the 2 people bald-headed, like this one. 2 people bald-headed. We have another one here. We have another here. As you may go on, you will be selecting, like here, you will select out those with the bald-headed. And then remember, if you move from one tree branch to another, you are going to add, because they are mutual exclusive events. And if you move across the branch there, along the branch, you will find it is independent event, because selecting of the first person does not influence the selection of the second person. So, because no routine or given rule is followed, so it will be that way. And if you work out, you will find out the given value. So calculate the probability, or find the probability that less than 3 are bald-headed. So less than 3 is either that 3 less than 3 is either 2 or 1 are bald-headed. Less than 3, so it is 2 or 1, not 3. So 2 and 1 are bald-headed. 3 are not bald-headed. 3 are not bald-headed. I think you understand that. And at least 2 are bald-headed. At least it means the least number of those people who are bald-headed are 2. So meaning it is 2 and more. So this will be 2, 3, and 4 are bald-headed. So you calculate them and you find using mutual exclusive event. With that, we have come to the end of our topic. I hope it has been interesting. Thank you for watching it. See you in our next video.